Welcome to this session of mechanical ventilation part 2. I'll request the students to see the first video part 1 so that we can continue with our discussion. So in this the learning objective is simple mode of mechanical ventilation as per the equation of motion, which we have discussed in part 1 in detail. The idea to understand the most common scalar, that is pressure time scalar, and what information it provides. We will try to analyze and understand the concept of stress index. We will also see how the resistance and compliance problem can be depicted from the flow time scalar, and then the word about the pressure volume loop and the flow volume loop. So let's go and first understand about the what we discussed in last session, equation of motion, and how the control mode of variables can be depicted from it. So we saw that there is if you consider the endotracheal tube and the airway as a tube, a single lung compartment model, and this is the alveoli, and we know that the pressure at the outer end here, the vent pressure, the ventilator pressure, or the P muscular, that is the diaphragmatic pressure, both tries work in sync to draw the air inside the lung, that to generate a flow, and this is equal to, depends upon the flow into resistance, that is the drop in the pressure as per the turbulence of the gas, and then as per the disease condition. In addition to it will be the volume inside the alveoli, that is ability of the alveoli to distend will be volume into elastance. We know that elastance is equal to 1 by compliance, it's a reciprocal of compliance, so you can also write volume by compliance plus the small amount of pressure which remains in the alveoli to prevent atelectasis is the positive and expiratory pressure. This we have discussed in detail in part 1. So if we see the two modes of ventilation, one is the pressure control mode. Suppose we see a pressure control mode as per the equation of motion. What happens? This P vent or this P muscle, this is under control. So in pressure control mode, the pressure is controlled. So pressure time curve, you'll see the scale wave pattern in pressure time curve, the pressure is controlled. And to maintain that, there is a decelerating flow pattern. In flow time there will be a decelerating flow. This is pressure time, this is flow time. Decelerating pattern will be there, and depending upon the resistance, whether it is high or compliance is low, the volume will be variable. So the volume will be variable depending upon the elastance. So if there is a low compliance, the lower volume will be delivered. If higher if the elastance or the compliance is normal, then the volume will be higher, will be generated. So what does it mean? That in pressure control mode, the left side is under control, so you have to keep a watch on tidal volume, which may vary in the ICU. We know that patient goes in fluid overload, or the tidal volume may come down, or if there is a change in resistance, the volume will be variable and there will be desaturation. So in this mode, keep a watch on the tidal volumes. Next is the volume control mode of ventilation. So in volume control ventilation, again to understand from equation of motion, the pressure at the end of the ventilator, P vent, is equal to flow. Sometimes we can depict the flow in the books as a V and dot, flow into resistance plus, we saw volume by compliance plus positive and expiratory pressure. So in volume control mode of ventilation, the right side is under control. So what is under control is the flow. So you have square flow wave pattern. This is a square flow wave pattern, this expression. So the flow is constant in the volume control. So volume control, you have constant flow. And if the resistance is increasing or compliance is changed, what you will monitor will be the pressure. So you will monitor the peak airway pressure and the plateau pressure in volume control mode of ventilation. We are not going in detail of the dual mode, which combines the two, but from equation of motion point of view, we can understand that if the right side variable under control, you have to monitor the left side. If left side in pressure control mode, you have to monitor the tidal volume. So keep this basic thing in mind before we move further. So let's come to the important alarm, which is the most common alarm you get to hear in the ICU. The patient on ventilator, and the most common alarm which you hear will be the pressure alarm. So let's understand the pressure time curve. Let me show you the components of pressure time curve scalar. Before moving to the pressure time curve scalar, I'll just show you the various graphs which are various ways which you should know. So if we draw a baseline, you should just know that patterns of waveform. This is the square wave waveform. With the square wave waveform, you see flow time curve. This is a constant flow in volume control. If you see this square waveform in the pressure time curve, it is a pressure control mode. So you can see the waveform from here. Then the other pattern you see is this is the ascending ramp pattern. This is your descending ramp pattern. This you see in flow time curve in the pressure control mode. That is a descending ramp. You can see the round pattern. This is the sinusoidal waveform. This you see in the patient with spontaneous breathing. And you see the exponential rise. This you see when the alveoli are recruited as exponential rise in pressure time curve, and this is the exponential rise, and then there is the exponential decay below the baseline, which may depict the expiration. So just keep these various waveforms in mind while we move further in understanding the various graphics. So first important to understand, as I told, is the pressure time curve. So let me draw the pressure time curve. So on y-axis we take the pressure, on the x-axis we take the time. So this is pressure, this is time. So what happens in volume control ventilation? So we know that the airway resistance will be there. If we keep a baseline pressure, say this P, this is start from 5 centimeter water P. So this is the baseline variable, and from here the pressure rises. The initial pressure rise will be because of the resistance in the airway, trachea, tube, bronchi. So this will be the initial airway resistance. Then there will be exponential rise in pressure, that is the recruitment at different time constants of the alveoli, and you will reach the peak pressure. If you keep an inspiratory pause here, there is no flow, there is a slight drop in the pressure, and what you see is the plateau pressure here, and then there is the expression to the baseline. This is the normal morphology of the pressure time curve. Now what happens if there is a increase in the resistance? So if you see a morphology like this, again pressure time, this pressure time, this variable pressure increases, and then inspiratory pause, it drops, and then somewhere it is plateau here, and this is the baseline. So if you see the increase in the peak airway pressure here and normal plateau pressure, which you can see at the inspiratory hold, and this difference is increased, so that means there is a resistance problem, and this helps you to find out the problem. So troubleshoot. So you can troubleshoot if there is a high pressure alarm and peak pressure is high but the plateau is normal. Here what you are going to do is you have to find out the cause. You start from your ventilator. You see the from the ventilator and auscultate the patient. Try to see whether there is a bronchospasm, whether there is a tube is blocked, whether there are secretion in the tube, whether sometimes the filter is blocked. So you can troubleshoot the resistance problems looking at this graph. In other situation, if you see the graph like this, the peak pressure alarm is high, you see the inspiratory pause, you draw the pressure time curve here, so pressure time, and you see that the peak pressure has gone high and all inspiratory pause, plateau is also high. So both peak and plateau are high. So definitely the problem lies in the lung here. So there is a compliance problem. There is a problem with the compliance. And what are the various problems can be there? There may be pneumothorax, auscultate the patient. There may be patient may be having a pulmonary edema, positive fluid balance, or consolidation, or ARDS. So you can, from these two patterns, increase in peak pressure and difference between peak and plateau is a resistance problem. If there is a not much difference and peak and plateau both are increased, then the problems lie with the compliance. So in this way, the pressure time curve help us to identify the problem in the patient and troubleshoot accordingly. Now let's try to understand about the stress index. So stress index, also from the morphology we can find out various things, like I told you initially. If you this draw the pressure time curve here, again pressure time, and I told you that the initial part of resistance because of airway, and then there is a tidal recruitment of the alveoli, then there is a expiration, this is expiration. So you have to see the slope of this tidal recruitment, and this usually you can see along with the flow time graphic. So we know that flow time graphic is a square wave pattern. In the square wave pattern you can see this is square wave pattern and this expression. So you see the square wave pattern, and if you take the midpoint of this and this and draw a line here, so you have to take the slope of this line. So suppose the slope of this line is flat like this is normal, and it is also depicted numerically, and it's normal between 0.95 to 1.05. This is the stress index which is normal. Now let's see what happens when there is a tidal recruitment or stress index is less than 0.95. So slope is less, or stress index less than 0.95. So what happens in this graph will be, this will be the inspiration, and you'll see the concave upwards and then drop and then expiration. So if you see this kind of picture here, concave upward, that means the stress index is less than 0.95. This is about the tidal recruitment. Sometimes if you see that this is the graph here, and you see that there is a tidal recruitment here, you see the concavity upward, and then it goes down like this. So if you see the concavity upward here, it's a sign of over distension. It's a sign of over distension, and the stress index is more than 1.05. So stress index alveoli is more, and chances of ventilator induced lung injury. So if you see that it is concavity upward, the stress index is high and is sign of over distension, and there is a chance that there might be ventilator induced lung injury. If it is concave upward, then it is a sign of tidal recruitment, and if it is flat or normal, it is between 0.95 to 1.05. So this morphology also you can monitor on the pressure time curve. On a pressure time curve, if you see that this graph, you see like this, lot of concavity downward, this also signifies that the patient's work of breathing, or patient is actively work of breathing is with the patient. So the inspiratory thing is here, so this is pulled down. So this signifies that the work of breathing is being done by the patient. You need to sedate, or you need to set your ventilator accordingly. What another thing, so you see that from pressure time curve, pressure time scalar, we can find out the resistance problem, we can find out the compliance problem, we can calculate, or we can know the about the stress index, over distension, tidal recruitment. What else we can know? So if we have this pressure time curve here, so if I again draw it, this is pressure, this is time, this goes up, inspiratory pause, plateau pressure. At expiration, I have kept a hold on expiration, and this slowly rises here. So this is my baseline positive and inspiratory pressure. Anything additional which is measured here is the auto P. This is seen mostly in the COPD patient. So dynamic hyperinflation. So you can find out the reason for auto P, whether your respiratory rate is high or tidal volume you have to reduce, or you have to increase the expiratory time. So pressure time curve also gives you the idea regarding the auto PEEP, and you can actually calculate the amount of auto PEEP here. So next we'll go to discuss about the important flow time curve. Now let's see I'll be interested in more in the expiratory limb of the flow time curve. So if we know that this is y, this axis shows the flow, and on this x-axis we have time, and we see that this is a constant flow pattern. Where do you see in constant flow pattern? In a volume control mode of ventilation, and expiration, as I told, passive exponential decay. Now this expiration flow pattern is common in both volume control and pressure control. So any mode it is common because it's passive. So from this expiratory limb you can have lot of information regarding the resistance and compliance problem. Let me explain that. So if this is the flow time curve, and you see that this is a flow, and during expiration, as I'm saying, the peak expiratory flow is reduced. So this is now less, and you see that expiration time is prolonged. So there is a prolongation in expiratory time and reduction in the peak expiratory flow. So this depicts your problem with the resistance. So patient have high airway resistance. So just looking at the expiratory limb, you can identify the resistance problem. Similarly, there are other patterns which will also give us clue. Like in expiratory limb, if you have something like there is an expression peak expiratory flow, and you see a lot of oscillations here. So this expiratory limb, this kind of pattern will give you clue that patient have lot of secretions or patient irregular oscillations. There is a time to do suction. So it is excessive secretions can produce this kind of picture in a expiratory limb. If suppose contrary to the first graph, if there is a expiratory limb shows that increase in the peak expiratory flow and reduction in the time of expiration. So time is reduced, peak flow is increased. When will happen? This will happen in when the compliance is poor. So stiff lung, it will quickly empty. So quickly empty, the peak expiratory flow will increase, and it will quickly empty. That's why the peak inspiratory time, so your expiratory time will reduce. So that's why you don't see auto PEEP in ARDS patient. We increase the respiratory rate up to 20-24 because these are stiff lung. They will empty fast and increase in the peak expiratory time and short expiratory time. So this is, if we see this pattern in the patient with a compliance problem or patient with low compliance. So you see that from the expiratory limb, whether there is a pressure control or volume control, the expiratory limb morphology will remain same, and you can identify so many problems from related to resistance, compliance, secretions. Now another one I will show you about the synchrony problem. So suppose the patient, you have kept the inspiratory time short, and this is the flow time curve, and in expiration you see that this goes like this. So and then again there is a upward deflection, and then there is a next breath. So these two deflections are the wasted effort of the patient. These are the inspiratory effort which were done by the patient, and they failed to trigger. So these are the failed trigger because you have kept the inspiratory time short, but the patient's neural inspiratory time is prolonged. So that's why the newer modes like neural adjusted ventilator are supposed to improve the synchrony. So you can see the synchrony problem here, and wasted ventilation failed trigger because of the short inspiratory time, and actual neural inspiratory time of the patient was prolonged. So this also can be depicted from the flow time curve. What else we can see from the flow time curve? So we can see the compliance problem, we can see the resistance problem, we can see the fail trigger. Suppose again you are seeing the expiratory limb is not touching the baseline, there is again the inspiration started, then there is the next breath. Similarly here you see that it has not touched the baseline. So this also signifies the auto-PEEP or dynamic hyperinflation COPD patient. So you don't need to press the expiratory button to see on pressure time curve the auto-PEEP. You can easily see in the expiratory limb of flow time curve without pressing any button. If you see that there is an inspiration before the expiratory limb touches the baseline, there is no complete exponential decay, and that will give clue to the patient is having the auto-PEEP. So these are the two important, very important pressure time and flow time curve. You don't get much of the information from the asset from the volume time curve, but yeah, so you can pick up the leaks from the volume time curve. So if you have this volume here and time here, and you see that inspiratory volume and expiration is lost, so there is loss of volume here, so there means there is a leak. You can pick up the leak from the volume time curve. Or in the peak alarm is set up high, the new ventilator, the ventilator have a protective mechanism, and the tidal volume will not be generated because the pressures have gone too much high. So you will see this kind of narrow low tidal volume in such situation. So this is about volume time curve. So now let's come to the last part, that is the loops. So we will understand two types of loop. One is pressure volume loop and the flow volume loop. So pressure volume and the flow volume, these are the two loops we'll try to understand. Now in pressure volume loop, volume is on the y-axis, Vy volume, and pressure on the x-axis. So any thing which you see here, if you see a sharp fin appearance, or there is a, you see that there is a clockwise motion, it is related to the spontaneous breathing effort. What that I mean, spontaneous trigger. So you see this inspiratory limb, and this is the maximum tidal pressure here. There is a lower inflection point, and then you see the expiratory limb, upper inflection point, and coming to the baseline. So if you see the clock, 3 o'clock, 9 o'clock, 3, 9, 12 and 6. So if you see this movement, this is going like this, so the anti-clockwise. So the machine breath is looked as an anti-clockwise here, inspiratory limb, expiratory limb. And if you see anything which is clockwise direction here, so this is a spontaneous attempt which will be clockwise. Now distance between these two will give us the resistance issue. So if you see this loop is becoming bigger and bigger like this, so this is known as hysteresis, and this is commonly seen in the patient with airway resistance problems. So patient with airway resistance. Another important compliance problem which you see in the pressure volume loop is the shift of the loop. So simply just see the shift of the loop, baseline and shift of the loop. So if I draw this loop here, so this is pressure, volume, and you see that this is inspiration, expiration. Now over certain days of time, this loop has turned toward the baseline. So more pressure is required for the inspiration and then coming to expiration. So this loop is shifted downward. That means the compliance has gone down. So the lung compliance is become poor. So that is the idea you can get from the pressure volume loop. Now coming to the flow volume loop, most of you who are pulmonologists or who has done the pulmonary function test will understand it quickly. So in flow volume loop, normally in ventilator, what we get is the inspiratory limb up and the expiratory limb below the baseline. So this is the flow on the flow, and this is the y-axis, and this is the volume you see here. So inspiratory limb will be like this, up above the baseline. Then there will be expiratory limb, peak expiratory flow, and will touch to the baseline. This is the flow volume loop normally you will see. So in flow volume loop, again expiratory limb, if you see the lot of oscillation, like in expiratory limb or flow time we have seen, it will depict that patient has secretions, right? Another abnormality quickly picked up on flow volume loop is the reduced peak flow, reduced peak expiratory flow. So this is inspiratory flow, and this is the scooped out pattern you will see. So scooped out pattern. So normally it should come like this, but it is reduced and there is reduction in the peak flow. And you give a bronchodilator and you get a normal peak flow touching the baseline. So that depicts the increase in the airway resistance. So you can easily pick up the resistance problem in form of this scooping pattern and reduction in peak expiratory flow. Suppose you get a expiratory limb which doesn't touch the original baseline here. So this is the flow here again, flow, get volume here, and during expiration it is just touching the back, not going to the where it started. So this will signify the leak. So there is a significant amount of leak which can be picked up from the flow volume loop. And if you see something like inspiration, flow volume, and expiration is touching here, so this is the amount of autopeep. So autopeep can also be picked up from the shape of your flow volume loop. So this is how the graphics in ventilator, when you are taking around, always peep in and look at the common pressure time, pressure volume, flow volume, and your flow time curves. That will give a lot of information and help you to troubleshoot and understand the various ventilator associated problems. For any queries, you can email me at practicaltips7@gmail.com. Thank you very much.